Continuity. A function is said to be continuous if there are no breaks, jumps, or holes on the interval being considered. Generally, when graphing a continuous function, we say that a function is continuous if you can draw it without lifting your pencil off the paper. The mathematical definition for continuity is a function f of x is continuous at x equals c if f of x is defined at x equals c and the limit as x approaches c of f of x equals f of c. So what that means is we're going to have something that's continuous if as we approach the value in the independent direction, the limit is equal to what we would get if we plugged that number directly into the function. So let's look at just a couple quick pictures of graphs that are and are not continuous. So if we're considering a function that's continuous, you may have something that looks like this. This function can be drawn without lifting my pencil off the paper and has no jumps or breaks or holes. An example of some discontinuous functions are piecewise functions that jump, so here we have a jump with a hole, or have asymptotic behavior. So here we can see a couple places where this function is discontinuous. So mathematically, if we want to show that something is continuous, we're going to use the definition. So let's go ahead and look at a couple of examples of how we'll study continuity on different functions that we'll look at in this class. Example 1. Use the definition to show that f of x equals 3x squared is continuous at x equals 1. Using the definition means that we need to show that the limit as x approaches 1, remember that's where we're interested, of 3x squared is going to be equal to the functional value at 1. That's our mathematical definition. So to show what the limit as x approaches 1 is, we need to consider the limit as we approach 1 from the left and the limit as we approach 1 from the right. So when we approach 1 from the left, we're considering values like 0.9, 0.99, 0.999. When we plug those into our function, we get the following values. We get 2.430 for 0.9, 2.940 for 0.99, and 2.994 for 0.999. So again, I want to consider what these values are approaching as I take the limit as x approaches 1 from the left. And so here, I feel confident in saying that these values are approaching the number 3. I want to do something similar to the right. I want to plug in 1.1, 1.01, and 1.001. When I plug in those values, I get 3.630 for 1.1, 3.060 for 1.01, and 3.006 for 1.001. So now, when I consider the limit as x is approaching 1 from the right, I can confidently say again that this is going to be approaching 3. So the limit as x approaches 1 from the left is the same as the limit as x approaches 1 from the right, which is 3. So the limit as x approaches 1 of 3x squared is also 3. So my question is, does that match the functional value? If I were to take 1 and plug it into my function, I would get 3 times 1 squared. Well, since 1 squared is 1 and 1 times 3 is 3, my functional value also equals 3, which means that this function is continuous at x equals 1. So that's how we use the definition. Now, most of the time that we're talking about continuity, we're not going to be doing it so formally. Instead, we want to get a good feel for whether or not we think something is continuous and look for signs that a function may or may not be continuous. So let's go ahead and try the next problem. Example 2. Determine where f of x equals 2 divided by x minus 4 is not continuous. So looking at this function, the first red flag I see is that in the denominator I have an x minus 4. I know that I never want to divide by 0, so I'm concerned about the number 4. So I'm going to make a note over here. Now, any other number I can think of, 0, 1, 5, 12, I can plug those all in confidently, and I know I can get a functional value. So there's nothing else on my radar that might be a red flag. If I consider the graph of this function pictured below, I can see that at 4, something really interesting happens. I get what's called an asymptote. So again, if I want my function to be continuous, then I need the limit to equal the functional value. Well, I know that there's not even a functional value that happens at x equals 4, so I know I can't be continuous there. But I can also support that with my limits, because if I consider the limit as x approaches 4 from the left, I am approaching this asymptote that shoots down to negative infinity. And if I look at what's happening from the right, it shoots up to positive infinity. Neither of those are approaching a functional value, and they're certainly not the same. So this function is not continuous at x equals 4. But everywhere else, I can see, both on my graph and through my testing, that the functional values will be the same from the left and the right. So any other point I pick that's not 4, I should have no problem, because the limit will match the functional value. So again, my intuition told me that I don't want to divide by 0. And then when I graphed it, it confirmed what I thought, because I saw this asymptote. And so I couldn't draw my graph at 4 without picking it up off the paper. So here, again, this function is continuous everywhere except for 4. Example 3. So let's take a look at a piecewise function. We want to determine where the following function is continuous. So we have x squared minus 4 if x is less than 0, and x minus 4 if x is greater than or equal to 0. So when we think about these functions, x squared minus 4 and x minus 4, there's not a whole lot of concern. We don't have anywhere that we're worried about plugging in any values. We don't have any denominators that might equal 0. We don't have any square roots here that might end up with something negative underneath. So we're not so worried about jumps and holes and bumps. However, because it's a piecewise function, we always have to worry about a jump happening right where the function is split. So here, my function splits up at 0. Okay, so when x equals 0, I need to determine if the limit is going to be the same from the left and the right. So if I look at this graph and I look at what's happening from the left, my x squared minus 4, as I approach from the left, the y value is going to equal negative 4. So the limit as x approaches 0 from the left of my function is going to equal negative 4. And again, when I'm approaching from the left, I'm considering x squared minus 4, because that's the function I consider when x is less than 0. If I take the limit as x approaches 0 from the right of f of x, well, now if I'm bigger than 0, I'm in the x minus 4 situation. And if I look at what's happening on the graph here as I approach from the right, that also looks like negative 4. I could confirm this by plugging in a couple values less than or greater than 0 into each function, and I will see that they both indeed approach negative 4. So since it's the same from the left and the right, then the limit as x goes to 0 of the whole entire thing equals negative 4. So we're going to be continuous here in terms of the limits, but we also have to make sure that that's true in terms of the functional value. So we know that the limit is negative 4, but I also need to know what happens when I plug in 0 into my function, just to make sure it's continuous at 0. So if I plug in 0, I need to go to the equals case, because that's the case that includes 0. So if I plug a 0 into the equals case, I get 0 minus 4, which also equals negative 4. So the limit is going to equal the functional value, and therefore is continuous at 0. 0 was the only place that I was concerned about. Looking at the picture, I can see there's no other discontinuities that I have concerned about. So here, this function is continuous everywhere.